The Amazon operates as planetary infrastructure. It functions as a massive storage vault, pulling carbon dioxide out of the atmosphere and locking it away in trees and soil. After reviewing 3 decades of climate data across the region, scientists have identified an anomaly that required a new scientific classification. They call the condition hypertropical. It describes an ecosystem pushed past its biological limits by hotter, more frequent droughts. Under this stress, the rainforest behaves like an overheated sponge left drying on a radiator. When drought bakes the ground, the support system of roots and moisture malfunctions. Instead of growing and absorbing carbon, the trees wither and drop their leaves to survive the heat. This shift reverses that flow. When the trees wither on a massive scale, they stop absorbing carbon and instead release their stored reserves back into the air, turning the forest into a carbon source. This system relies on a process called transpiration. The forest effectively sweats, releasing water vapor into the air through its leaves. That vapor aggregates to form clouds, returning as rain. The rainforest maintains its own closed water loop. Severe drought weakens this loop. When trees are too stressed to transpire, the vapor supply halts and the cloud cycle breaks down. With fewer clouds, the forest receives less rain. This creates an even drier environment that further weakens the remaining trees. This is a runaway feedback loop. The forest stops protecting the atmosphere and starts fueling the very conditions that cause its destruction. Runaway climate conditions have historic precedent. Earth's geological record contains several examples of what happens when these planetary feedback loops break. During the snowball Earth period, ice stretched almost everywhere, possibly reaching all the way to the equator. This was driven by the albedo effect. Because ice reflects sunlight like a mirror, the Earth absorbed less heat and cooled further, which allowed even more ice to form. The freeze fed itself. Breaking that cycle required massive volcanic eruptions. As volcanoes released enough carbon dioxide to trap heat, the planet began a violent transition into another extreme. This created the hothouse Earth. In this warming loop, shrinking ice sheets left behind dark oceans that absorbed more heat. The water expanded as it warmed, digging the planet deeper into the heat zone. These warming loops often lead to ocean anoxic events. These are periods when massive regions of the ocean lose their oxygen entirely. Warm surface water stayed on top, while deeper water stopped mixing and refreshing its oxygen. Bacteria took over the stagnant depths, rotting organic matter and collapsing marine ecosystems without the need for an external trigger like a meteor. These runaway loops leave physical evidence across the globe. The decaying swamp forests of ancient hot periods eventually compressed into the coal deposits extracted today. Many ancient climate shifts were driven by different continental layouts. Massive monsoon systems, for example, required a single supercontinent to disrupt global winds and moisture. But the Amazon is shifting into its hypertropical state now under our current planetary configuration. The heat waves and extreme droughts recorded today serve as the baseline for the next century. Today's disaster seasons have become tomorrow's average weather. These conditions will not be confined to South America. Researchers expect similar hypertropical conditions to emerge in parts of Africa and Asia. As the forest slips from a carbon sink to a carbon source, it mirrors the ancient runaway cycles. It stops protecting the atmosphere and starts fueling the very problem it once controlled. Earth has transitioned through extreme loops many times before. The planet will eventually adapt to these new rules, but the specific, stable climate that humans evolved in will not.